Today, we are really starting chapter 6. So what we did last time was just use the calculator so that we can speed up our process here. And what we're trying to do now is look at some applications of our integral. And so we don't want to spend a lot of time calculating the integrals. We want to figure out how can we use them and what things can we use them for. So today, we're going to find out how to find the area between two curves expressed as a definite integral. So we just have two functions here. We have our f function and our g function. So in this first graph, what is this shaded area showing us here? Or how would we find the shaded area?
You do the graphy thingy and the number and the 7 and the thing.
Okay.
The area below f from A to B.
Okay, the area below function f from a to b. And how do we express that as a definite integral?
Well, that's A, B. A on the bottom. B
A on the bottom, b on the top, right?
Integral of f of x from a to b.
Wouldn't have to be plus the integral of a to b of b.
Yeah.
Okay.
They're two.
So in this example, the shaded area is the entire area below f of x. And so this one will be given just with this. You don't need to add anything to it. Okay. Now in this example, okay, this is our g function here. So how do we express this shaded area? Okay, so that's what we've been doing up until this point. Now, what we're going to figure out today is how do we find just the area between the function of those two graphs?
F of x minus g of x.
There we go.
God, I'm smart.
So you can see right here, if we compare these two, the only difference is it's this area take away this area, which is right here. And so we can just go the area from a to b of f of x dx minus the integral from a to b of g of x dx. Okay. Now we're going to look at this in another way. And it's kind of using our idea of those representative rectangles. Okay. And we're going to just take any x in that interval from a to b, and we have a rectangle here. Now, the area of a rectangle is BH, the base times the height. Okay, so what is the base of this rectangle here? From here to here. It's just from this x to this x, and we're just going to call that delta x. And then if we look, what is the height of the rectangle? Well, this right here is g of x sub I, and the height here is f of x sub I. And so the height is really the difference of those two. Okay. So our area is really the height, which is f of x sub I minus g of x sub I times delta x. Yeah, so it's f of x sub I, which is this height, minus g of x sub I.
But what's this I thing?
I is just any x on the interval. And then we talked about the fact that it's the sum of all the rectangles as we let, the limit of the sum of the rectangles as we let delta x go to 0. And so what we can do is we can combine these two here.
Wait, what's the rate of change in x?
Okay, so there's kind of two different ways of thinking about it there.
What's better to think about in the second way or the first?
I like thinking about it this way. However, it's going to be helpful to also realize what the rectangles are and where the rectangles are and which way they're going. Okay, and we also know, right, from our properties of integrals that since these limits of integration are the same, we can just subtract the two functions right here. Okay, and so you can see here, that's the definition that we just came up with. All right, it's exactly the same. And the stipulation here is that f of x has to be bigger than g of x on the interval. Okay, so you have to take the larger function minus the smaller function. And that's what we got to make sure that we do here. So let's try example 1. Now in this case, it says find the area of the region between the two curves. So it's going to give you two functions and then a region. So we want this from 0 to 1. So let's go ahead and shade that. Okay. And sometimes I like to label which functions are which graphs. So the top graph is which one? F of x. That's definitely x squared plus 2. And then the bottom one is g of x. Okay. So if we want to find the area here, it's going to be the integral from 0 to 1 of x squared plus 2 minus negative x dx. Now notice I put my second function in parentheses. You don't really have to put your first function in parentheses. Okay? And yeah, because as this becomes a binomials, trinomials, you have to remember to change all the signs. So all in all, we're going to have x squared plus x plus 2 dx.
Why do you subtract it?
Okay, so just coming back to this, we have, here's the integral under f of x, and then here's the integral under gx. And if we want just between the two functions, we have to subtract out the gx area. And so that's what we're doing right here. And you can see that the integral here will give you a negative number, right? And so if we're thinking area, if we subtract the negative integral, then it's actually going to add to the area, and it's going to work. All right. Now, we can use your calculator just like you were doing on your quiz. Okay. And then you can hit math frac, right? So function integral.
Why do you want to?
Oh, should we always try and math that?
Yeah. If you can give an exact answer, then that's going to be better. Okay, so then just math frac 17 over 6. Okay. Now, what I've done for you is actually graphed y equals x squared plus x plus 2. Okay, so what we're saying here is that this shaded area is actually equal to this shaded area. And let's see.
Well,
I did this at home, so I wonder if Well, my graphs are a little bit different size.
Is that pasta?
It's pasta.
Oh, you're clever.
Okay. So
Jessica.
where is all the pasta coming from? So just so you can see, each pasta thing represents like a rectangle. And it's going to be close.
Like, you're so precise.
I did this on... Okay. Well, which ones did I mess up on?
It's alright. We get the idea.
Is it close enough? So you can kind of see there how this pasta equals this area. Now, if I go ahead and move it over to here, just roll them all over. And then we realign the bases on the bottom, which is kind of hard to do with angel hair pasta.
Use spaghetti.
I should have used spaghetti. Okay. Then you can see that it's going to equal the same type of thing. I gave it a shot. But you can kind of see how it works there. So it's basically like, if you can think about this, if you could take this function, right, and all of these rectangles were fluid, and you raised this up, then it would give you this graph right there. So it just flattens out the one, raises up the other function.
Oh,
So
the bottom triangle went over there.
yeah, exactly. All that bottom triangle goes into this little extra stuff here.
Oh, get it.
So it's kind of a cool representation. Not really necessary to do the problems, but anyway.
Oh, so that would be like the
This is the subtracted function. All right?
But it's the same thing.
But it's the same thing. So here we go. Let's try our next one. Now we have our two functions.
It's something like x cubed
Mhm.
and x squared plus 2, and then the x cubed ends up taking it over, going, because the x squared would be flat, or
Yeah.
the x cubed would end up crossing.
Right. We're going to look at those in the next couple examples. All right? So now we're still just between a region that's defined for you. Okay? So here it's from -1 to 3, so go ahead and draw the area we're looking for. Okay. And then we know that our top function is 0.5 x squared plus 2. And the bottom function is 2x minus 3. So our area is from -1 to 3 of 0.5x squared plus 2 minus, in parentheses, our second function, our bottom function, 2x minus 3 dx. Now, even if you don't trust yourself with doing this subtraction, you could type this straight into your calculator and it'll still give you the right answer, right? If you want it nice and neat, you're like that neat, free, perfectionist type of person. Easy now.
Okay.
I like to see it as one function, or as a simplified here. Okay, and just get some more practice here. Math 9, 0.5x squared minus 2x plus 5 with respect to x from -1 to 3. Okay, and we'll do a little math frac. 50/3. Okay, so that's how to do it when the region is defined for you. Let's move on to page 2, shall we? We shall. Leave that right there just a minute. So now we want to find the area of the region between two intersecting curves. So when we look at these two curves, we can see they intersect here and here. So the area that we're looking for is right here. And when we look at this, here, if we were to draw our rectangles, we would draw vertical rectangles. Okay? When you draw vertical rectangles, the limits of integration are going to be from the left point to the right point. Okay? So we've got L and R. And then your functions, it's going to be the top function minus the bottom function. And this is the examples we just did. And when it's this way, it's going to be with respect to x. So your functions are going to be in terms of x. And that's an important note right there. That's going to match. Okay, we can also do this when we would have two curves that we would find using horizontal rectangles. Okay, so we're going from this point to this point, and this is our bounded region. And in this case, notice if we did vertical rectangles, it really doesn't make sense because you can't really find the integral, right, if that's your function, because it's not really a function of x. It doesn't pass the vertical line test. Okay? So what we do is we turn this on its side, and we actually look at horizontal rectangles. And then we turn the whole process on its side. So now our integration is going to be a function of y. Okay. And we need it with respect to y. So we're going now from the bottom to the top. And these are going to be actually not this way. Since this is with respect to y, your b is actually going to be right here. And the top is actually going to be right here. Does that make sense? So since it's with respect to y, our b and our t, the limits of integration, are also y values. Okay? Then the right function and the left function. So this is the right function. And this is your left function. Okay? We'll see some examples of this, so shouldn't be too hard. So let's take a look at our first one. So when we look at this, we're going to be able to use vertical or horizontal rectangles. Vertical, okay? So we want to find the area here. So let's go ahead and shade that in. And then I usually like to draw a vertical rectangle. And I want to label my functions. So this is my f of x. This is my g of x. And since this is a vertical one, we actually want to find this x value and this x value here. So the points of intersection is exactly right. So to be able to find these points of intersection, we set f of x equal to g of x, and then we solve.
Do we use?
Yeah, sure. We'll show those in yeah, let's do that in this example. Why not? We don't want to eyeball it, all right? Because it may not work. So one of the functions here is 2 minus x squared. The other function is x. Now let's just zoom standard here. Okay. Now to find the intersection points, we're just going to go second calc, intersect. You pick your one curve, you pick your other curve, and then you guess. And it's -2, -2 for one of them. And then we do the same thing. So second calc, and we want the intersect. So one curve, then the other curve. And remember, you can see what the curve is up here. And then we're going to guess. And we get 1, 1 for the other intersection.
All straight lines.
Yeah. Okay. So that's one way of doing it using the calculator. I think in this case it's probably even faster to just solve it, right? Minus x. So we have -x squared minus x plus 2 equals 0. Take out the -1. Factor it. What is this? X plus 2, x minus 1. So x equals -2 and positive 1. And we only care about the x values here because that's just our limits of integration. So, you know, don't become so calculator dependent that you don't know and understand how to do this. So what we're looking for here is our integral from -2 to 1 of our top function, which is f of x plus minus our bottom function, which is x, and with respect to x. Now let me just rewrite this here. It is as simple as it gets. But I want you to think about this and consider this. How this here and this here look exactly the same. So in the process of solving where these two are equal, you're actually getting the function that you want here. Okay, so could even just save you some time just to take this and input it right there. That'll work for all of them that are f of x and g of x. It's going to work out. Okay, and for our calculator then, we just have math 9 negative x squared minus x plus 2 respect to x and -2 to 1. You got 4.5 or 9 over 2, either way.
So do you think there's a decimal like 4.5 or something like that?
That's fine.
But then down 0.333.
Yeah, then do the fraction. All right, so let's take a look at our next example. Here we look and we see our functions are in terms of y. G of y equals 3 minus y squared. And so that's graphing here, g of y. And then this one here is y plus 1. So in this case, our area is from this point to this point. And our rectangles are going to be flat or horizontal. Okay. So first thing we need to do is find our limits of integration. This one would be a little bit tougher to use your calculators, right? Because you only have y equals in the graphing calculator, you don't have an x equals, which is what you do when it's a function of y. So we are going to solve it like old school.
It's the same thing.
And we're going to subtract the y plus 1. And then we'll rewrite it. Factor out a negative. And then we do get the same factors here. Okay. Now notice we got y equals -2. So when we look at this, is that the x-coordinate or the y-coordinate of this point?
Y.
It's definitely the y-coordinate. So Jackie, if you were talking about eyeballing it, right, you need to make sure that you choose the y-coordinate right there. And then this one, you can see the y-coordinate is 1. So this one is going to be the integral from -2 to 1, so from the bottom to the top, of our right function, okay, just 3 minus y squared, minus our left function, which is y plus 1. And this is going to be with respect to y.
If we just, like you said earlier, plug in the minus y squared and y plus 2.
Yep, that's exactly what you can do. Okay, so if you're comfortable doing that, go ahead and plug that in. Now, when we use our calculator, you don't have to worry about the variables are all y's. You still just use all x's, and it's going to work out the same. Okay.
Oh, and then we just
So instead of using the variable y, use the variable x, and we've already solved this one. And we have the same thing. Okay. A couple more examples. We'll start to move a little bit more quickly, because I think you guys get the concept, right? All right. So in our next example, we want to find the area between the intersection of the two curves. So in this case, we're going to have to break it into 2 parts. So you can see when your functions cross at more than 2 places, like 3 in this case, we actually get 2 different regions that we're finding. So I'm just going to call one of these area 1 and the other one area 2. Okay, now we do have to find our 3 points of intersection here. And again, you can choose to use your calculator, or you can solve it. Either way works for me. You want to race? You use the calculator and I'll solve it. Ready?
Do it.
Let's go. What? You can't start early. And you can't just eyeball it. That's not very mathematical. I did make very nice graphs for you, didn't I?
They were very
I did make very nice graphs.
precise.
Difference of squares. There we go. Anybody else finished on the calculator yet? Same? Okay.
I did the check.
So we do have x equals 0. Oh, not right there. This is x equals -2, 0, and 2. Okay, so really what we're going to have here is two integrals. So to find our first area, it'll be the integral from -2 to 0. Now in this case, we didn't label our functions yet. Which one is this one? That's f of x, because the cubed function we can see has the two changes in directions. And then this one has to be g of x. So a sub 1 is going to be f of x minus g of x. And didn't we already figure that out? 3x cubed minus 12x? Okay. Math 9. X, 3x cubed minus 12x with respect to x from -2 to 0. We get 12. And then for a sub 2, we're going to want to go from 0 to 2. And now we're going to switch it around, g of x minus f of x. Now if we just switch this around, subtract the other way, we can basically just take the negative of what we did here. Because they're just switched. And so we're really just subtracting the other way. Okay, does everybody see that?
Yeah.
So we really have 0 to 2, 12x minus 3x cubed. If you don't see that, go ahead and just subtract them like normal. You're going to come out with the same answer. You'll be fine. Now if we think about this in terms of area, if all we did was change the negative, right? You could factor out a negative and the area is going to be the same. And so this is really, yeah, so the total area is going to be the sum of the two smaller areas.
Now, is this area always going to be positive?
Area is always positive, definitely.
So we had negative space for stuff under.
But if you did the function integral,
That would be 12.
we'll just change these negative, positive, and we'll do 0 to -2 or to +2. Still gives you +12. Okay. All right. Oh yeah.
No.
There's also a couple things.
So that you'll get taped up on the side.
Okay. So for our next one, here's a place where, you know, if we look at sine and cosine, this is just going to keep repeating, and we're going to get a bunch of equal sections of this amount. And so we're just going to want to find one of these sections.
Just as a question,
Mhm.
each time it switches, it's just mirrored over that intersection.
Exactly. And so each one of these, you know, this one will just flip over this line, right? And so we're going to get a bunch of these sections that are equal here. So to be able to find this, we need to get our x coordinates, right? And so we're going to just say, where does sine x equal cosine x? Go to your calculator. That would be a good place to go.
75 and 3.9.
Okay, and how did you get those?
5 by putting them in and then finding the intercept.
So you graphed them?
Yep.
Okay.
You need to be more precise.
So we're going to go sine x and cosine x. Should we just go zoom trig? Might as well. Ooh, so pretty. Okay, and so we want to go from here to here. It is pi over 4 and 5 pi over 4, actually. Okay, so let's see. So I can calculate intersects, first curve, second curve. So we get 0.785. And then for our other one, second calculate intersect, first curve, second curve. And 3.927. So if you're not going to go exact, okay, go out at least 3 decimal places here.
Sine something. Let's see, sine of 0. Cosine is your right?
So yeah, this one's the sine, and this one's the cosine. So it's going to be sine x minus cosine x.
Sine of 0 is 1. Oh, no, sine of 0 is 0.
Yep. All right, and now we can use function integral. Math 9. Sine x minus cosine x. We got 2.828.
Jackie.
So that would be
It'd be 6.
yeah.
You could find the exact
A
thing.
lot.
So if you wanted to solve this, let me just show you how you do it by hand. You divide by cosine x. Sine x over cosine x is tangent x. Cosine x over cosine x equals 1. Do you know where tangent x equals 1?
X is a 45 to 1.
So pi over 4 would be one of them. And then the other, happens every 1 pi actually. So this one would be 5 pi over 4. And then you could actually find the real integral, but 2.828 is good enough for our purposes. All right, how you doing? Hanging in there? We got one more example for you.
We're gonna end like perfectly on time.
It's going to be perfect. So here we want to find the area bounded by 3 functions. And so we're going to find this area right in here. All right. And so we are going to do this by splitting it up again. Yep. We're going to split it up right on the y-axis. Get our first region, and then our second region. And I'm going to go ahead and just label the curves here. This one's x cubed. This one's negative 1/2 x. And then this one's x plus 6.
Just back on number, do B, letter B real quick. Since it's repeating, wouldn't it end up having an infinite area between them?
Right, so basically each one of these sections will have an area of this. So that's what the question was actually getting at. All right. So back over here. Anybody get the points of intersection yet?
Negative 4.
Negative
Negative 4,
2,
0,
So negative 4,
0, and
0, and
2,
1.5.
1.5, 2, 2.5, 2, 1,
6.
in a range from 1 to 2.5,
I think it's
I'd
at
say.
2.
Okay.
No way, that's a 2. Your graph is off. No.
Okay, so our first area.
It's not straight up. Angle straight. I'm gonna find out for you.
So sensitive.
Why do we have two, are those two areas for each of the different chunks of it?
Each of the different chunks, because right here it hands off from one function to the next.
I'm so thirsty.
So x minus negative 1/2 x is 3/2 x. Well, from the interval negative 4 to 0, it's just these two functions. Aren't you glad we can use the calculator for this?
These two.
Wait, x minus 1/2 x is 3/2 x?
Minus negative 1/2 x.
Ah, haha.
See, I told you it was 2.
What did I do here? Yes, we need our. So we got 12. And this one. I just went in and, oh, you subtracted. It's pretty easy.
So if the intersection for the bottom one wasn't on 0, then you wouldn't be able to do it.
Wherever the intersection is, that's where you'd go to.
That's where it's not.
So wherever the intersection is, that would be our
That would be-
splitting point.
We
Yes.
divided there because of the y-axis. We divided there because of 0, 0.
Exactly. Exactly.
Must have been.
Now, the only other thing I want to comment on is on your horizontal ones. Okay, this was nice and neat because they gave you the function in terms of g of y. Now on your homework, they're going to give you the functions in terms of x. So they're going to say g of x and f of x, but they're going to have horizontal things here. So all you have to do is solve the function for x. And then that becomes your function in terms of y.
Oh, I
Okay,
get it.
so give them a try. Check out the homework. It's already online, so you can see what I mean when you get there. If you have any questions, let me know.
I actually like this chapter.